use the algorithm to predict human mobility patterns. It's kind of novel to use like machine learning model, simulated learning model, or transformer-based model here. And my name is Anjali. I'm from National Georgia University. I'm doing a third-year undergrad. So yeah, undergrad, high student. All right. So without further ado, let's dive in. Regarding our introduction, all right. So our test is quite simple. We have like several cities. We have 3 cities, and we have the users in the corresponding city. Our goal is to predict the last few days of data using the previous few days of data for training. And I mean, in many cases, people might turn to transformer-based models, such as burst or GPT models, and they pass in the data to the model and expect or end up with a good performance or result. However, our approach offers a different perspective. We began by observing the data characteristics, and we could define some insights from the observations, so we can get all the information we need to add structures or adjustments to the model, so we can have a model that is more tuned and like adaptable to the task, and that could lead to a better performance, I guess. All right. So some of you guys might be wondering why we chose K for the selected method. Well, the key actually lies in the data. We found 3 major data characteristics from the data, and we add 3 big additions, and which of the additions is specifically designed to address the data characteristic problems. And we add the addition to the K-news model, so that is like with more additions and different from the traditional like K model. All right. I'm gonna let another presenter to detail the data characteristics.
Okay, so I'm HuMob, and I'm going to talk about the characteristics of the data. After our analysis and observation, we found there are some characteristics of this data. The human mobility data have 3 major characteristics, which is time fixedness, flow contingency, and the flow uniqueness. The first one is time fixedness. It means that the people may go to same place at the same times. For example, just think about yourself. You may go to school or office during the working hour. After you leave the office, you may go back home and stay until tomorrow morning. This diagram shows the user's behavior. The x-axis is the hour of day, and the y-axis is the day of week. The darker area means that the user has a higher chance to appear at the same place at the same time. On the other hand, the lighter area means that the user may go to different places. As you can see, from midnight to morning shows the user may stay at the same place, such as home or dormitory. The second characteristic is flow contingency. It means that the user may go to some places where it's unusual for that person, caused by some additional situations. Thus, their schedule won't remain the same forever. For example, some people may go to KFC for Christmas or go to a restaurant for some special birthday party. This behavior won't appear often. The next one is flow uniqueness. This one is very easy to understand. It means that everyone has their own schedule or routine. So it's hard to use otherwise data to predict the movement. For instance, after they leave school, someone may just commute home, and someone may go to store to buy some goods, while others may hang out with their friend in the park. They all have different activities to do. Okay, so these 3 are the major characteristics of the human mobility data.
Alright, so moving on to the 3 big additions. As I mentioned before, we're gonna have like each of the additions that is specifically designed to address the data characteristic issue. So first, to address the flow contingency problem, we have an array filter. It's like we have like some blank markers on the left diagram, and that is like the common locations, which means that the user visited these places quite often. And we have some red markers here, which are incidental locations. It's like user went to these places not quite often. And what we did was to simply remove the red markers. So it's like we can remove outliers, and the model can focus more on the general trend and the places that have been visited by the user quite often. So So to address the second time thickness problem, we have the time segmentation technique. For example, like from the graph we've seen before, we have the darker areas, which are the more focused areas. It's like users have more regular activities during those hours. In the middle, we have the more spread out areas, which means that the user go to these places, like different places, and have more uncertain behaviors. So what we do is to simply divide the data by times. Just like the model can more concentrate on the data based on the historical records. Like if the user have more uncertain behaviors during certain hours or during certain timestamps, the model can yield the relevant predictions using the historical data. And for if like the user has more regular behaviors, like in the morning, probably stay at home or stay in the dorm, like the model can give more focused predictions. Alright, so by the way, we store them in the hash map, and the model is going to be trained on the data segment. So like for each time interval, we have a model trained on that data, and we have like, we're going to have a lot of models depending on the time intervals. Alright, so to address the final problem, we use flow uniqueness. We have individualized models. The logic is pretty simple. We build each model for each user. For example, like somebody have irregular behaviors, they might go to different places quite often. Like some people might stay at home all the time. So if we build a model for each person, like the model can effectively capture that person's behaviors, and that won't be affected by other users' trajectories. If their like behaviors or trajectories all weird or a little out of control sometimes. All right. So let's talk about the advantage of our proposed model, which is TT-CAN, like Temporal-Trajectory-based k-news model. The first one is pretty fast because, as we mentioned before, we segment our data based on the time, so we have a few pairs to compare. You know, like the k-news neighbor model compares like different nodes to calculate the distances, but because we have a few pairs to do the computation, the algorithm runs really fast. All right. So the second advantage is pretty simple because we only add an outlier filter and we create the hash map for each user and for each timestamp. So we don't have like a complicated structure like the bird or something else. It's like pretty easy for like a beginner or anyone to implement. All right. So the third one is it's pretty explainable. Unlike bird or other transformer-based models, like if you want to know what the model has learned, it's quite difficult for you to visualize them. But if you use a k-news neighbor model, you can simply plot the range. Like for that timestamp, you have a lot of nodes. You can plot it out to know like the user behaviors in that specific timestamp. All right, let's talk about experiments. So we're going to use the 2D model as the computer method. As you can see from the table, our TTM model has a higher change score and a lower dynamic time walking score, which means that our model performs better for this training data set. Oh, by the way, like because we don't have enough time to test our model across all the cities, so this one is also it's only for CDP. So for this case study, we have the blue markers, which are the actual locations. We have the red mark, and we have the green markers, which are the DD-generated locations. And finally, we've got the red markers, which are the DD-generated locations. You can see more overlap between the green markers and the blue markers, which shows that our model performs better than the DD-generated like one for this user in the case study. About our conclusion. So to address the first data characteristic problem, which is in homogeneous location, we split the data by time. To address the second problem in frequent locations, we add an outlier remover, and to like deal with the third problem, distinct trajectory problem, we implement an individual model for each person. Alright. So I want to promote myself a little bit because I'm interested in PhD programs like after I graduate. So if you are interested in my research or myself, you can scan the QR code or contact me through email. Thank you. All right.